Okay, since we promised to do the double slit, and I actually do enjoy this calculation, we're going to actually finish it. However, I'm not going to struggle through the calculation. I've actually already written everything out, so we'll just sort of walk through it. It's very similar to the last calculation, just a little bit more complex. A reminder of this, first of all, a reminder, this is the double slit where the slits themselves have a finite width, right? So we're not using the idealized eigenkets. We're using the idealized eigenkets, but we're not claiming to be in the physical state represented by the idealized eigenket, right? That's what we're doing. So, and as a reference, this is the paper that I'm sort of duping from, Quantum Interference with Slits by Thomas Marcella. Really nice paper. And so you're not going to see too much difference from this. If my explanation isn't good, go right there. Go right there anyway. I think this is a really good explanation and review of all of these things. Okay, so same setup as before, but let's look at the slits, right? The slits now have a width, and we're going to call the width A, but the center of the slit up here, and the center of the slit here, right? This will be, we'll call this one Y1, this one Y2, and the width of each slit is A. So they're the same width. And as we remember from the last lesson, we can expect that there's only one relevant dimension here, right? Well, one physically relevant dimension. There are some key dimensions. We should talk about one, which is namely the separation between the barrier and the screen. What's interesting is when you draw it this way, you kind of ask yourself, well, to get to this point, I have to go at two different angles, don't I? Right? Why am I just characterizing it with one angle? So you have to have D large enough where the difference between these two angles is not really significant, right? So that is something to think about. D should be large enough where we can treat the diffraction as though this is a system of slits. The way the paper describes it, this is a system of slits, and you have your incoming wave like this, and it diffracts like that with an angle relative to this entire system of slits. So that's how we look at it. And but it's otherwise the setup is just the same, right? But both slits are the same size, and they're separated by a distance, and that distance is going to be y2 minus y1. I'm not sure how the math worked out. The math might have had this one being y2 and this one being y1, not quite sure. But regardless, we have two slits. They obviously have a distance between them. In fact, why don't I just protect myself and just say the width between the two slits is d. Okay, so now in this circumstance, when the incoming plane wave arrives at the barrier, we know that if you make it to this side of the barrier, this barrier filters out all of the states except for the states that allow that have the particle inside the two slits. So just as before, we create the wave function that satisfies that condition at the barrier. So let's begin with that. So the wave function, so the state, right? I'm not going to call this is not a wave function in our language. It can be understood as a wave function given this caveat, right? Which a state when it's decomposed into the position basis, the wave function appears, right? But this is just the state, the kets of the general state at the barrier. And it's going to be composed of two parts. The part where it's positioned in the first slit, which I'll call psi, and the part that's positioned in the second slit, which I'll call gamma. So the gamma part is, say, we'll call that one the psi part, right? And that one not gamma, omega part. And the whole thing is omega, has this 1 over square root of 2. Now, we know how to construct, so it's a superposition of those two states, right? So it's normalized with 1 over the square root of 2. And we know how to construct each of these. We did that in the last class, the last lesson, right? So we know that the position representation of the state psi, which is what this is just this uniform distribution over the slit itself, which is now y is allowed to be between y1 minus a over 2 and y1 plus a over 2, right? That covers the whole slit. And it's 0 everywhere else, and this will be normalized. And likewise for gamma, same thing. The only difference is we're now centered at y2, but it's the same normalization and the same function. So when I write this down, I could make the limits to infinity, right? But I know this function kills it past a over 2 above y1 and a over 2 below y1. So I'm sort of looking ahead a little bit, and I'm trimming this integral to those limits. However, this integral here could definitely have been written plus infinity, minus infinity, or all real numbers, right? But once you make the substitution, this substitution into here, right, this 0 part kills everything outside of this range. And the same is true for omega. All right, so let me, So we construct omega the exact same way. The only difference with omega is, of course, the name of the state and the little 2 here. And then we ask ourselves the question, what is the probability amplitude of a momentum y for our state gamma, which is we're going to find the inner product with the bra py, p sub y, or momentum in the y direction is what that means. And so we just apply that bra linearly straight through the right-hand side. And with our substitution for omega and our substitution for psi, the two parts of the wave function, we now have this amplitude expression. So right now, this sum is where the interference is going to happen, right? This function and this function as functions of y is going to start having positive and negative additions and subtractions. This is where the interference happens, this sum, the addition of these two functions. We have not calculated the modulus squared, right? And the modulus squared is going to be the modulus squared ultimately of this sum, and that's going to be our probability density, right? So the difference between a circumstance where interference exists and where it does not is that it wouldn't exist if our prescription was to do this. Then there would be no interference. There would be no possibility of interference, unless, of course, there was interference in here, which there is, right? We've learned that from the last class, right? If you have a finite width, you have this Fraunhofer diffraction pattern. Gee, I hope I said that right. So take note. This is where the interference happens, in this calculation of the amplitude. All right, so now we're going to blow this thing up, right? So blowing it up is not very difficult because we're going to use the Jacobi operators, right? That's this guy right in here, right? And we're going to integrate this function over dy, and we're going to have the wave function is going to be over here, and then this, this is a wave function too, right? This is the ideal, the y eigenkets wave function in the momentum representation, and this is the slit 1, the double slit. So this is the first slit's wave function in the position representation. And we know what this is, right? Because we've built it, right? We said it's got uniform probability of being anywhere in that slit, and we've normalized it correctly. So that's all looking good, except that it's kind of getting tricky. So now the omega is the second slit, and I put that one in green. The only difference here is this 2, right? We're now centered at y2, which is different than y1, right? It's the two different slits. And we complete the same integral, but it's really the same mathematics. The key is this y2 is going to show up in the answer, and y1 is going to show up in this answer. So now we make the known substitutions, right? We know what this guy is, right? That guy is simply 1 over square root of 2 pi h bar e to the minus, or is it plus? E to the minus I p y y over h bar. We calculated that several times before. We very proudly did that without the Schrodinger equation. We did it just from the translation operator. Remember that lesson? And then this guy is our known function, which is 1 over a squared, where the limits have been applied already, because it's 0 outside this boundary. So, and the same is true here. There's no difference here except the boundaries, right? This is the exact same integral as this. The only thing that's different is the boundary. So when we do this substitution, let's see what happens. We pull out this 1 over 2 pi h bar, which is the normalization, and that's true on both of them. We pull out the 1 over a because that's this wave function, our slot wave function. And then the integral is fully identified, and it's a simple little integral of just an exponential function. The variable of integration is dy. So what's going to be left behind is momentum. And the same is true here. Again, the only difference being the location of the slit. So let's see, what next? So next, I think I rewrote that integral right here. So now we simplify it a little bit. Oh no, we execute the integral. So when you execute the integral, what happens? I think I did a little bit of simplification here. Let me see. Well, first of all, I combined this root 2 here with the root 2 of the overall wave function. By the way, if somebody ever goes and reads the paper and follows the math in the paper, I feel like the paper drops this root 2. So my final answer is not scaled the same as the paper's final answer. And I feel like I may have missed it or something else, but I feel like the paper dropped this root 2. So if anybody could check that, I'd appreciate it. But regardless, I could be wrong. I mean, I kind of did this pretty quickly, but I tried to do it separately and then compare. And when I compared and I traced the difference, it seems to come down to a root 2 that I either added or he omitted in his paper. So regardless, but I think this is pretty precise. This root 2 here is the normalization root 2 from the original wave function here. It's that root 2 that I'm talking about. So that's that root 2. This root 2 comes from this function and this function, pulling it out. It's part of the normalization of our plane waves. And then this 1 over alpha comes from the wave function at the slit, right? So now the two root 2's combine to give you 2. Then what's left is the square root of a pi h bar. And then the integral gives you I h bar py, right? That's from the integration activity, finding the antiderivative. And then you just are subtracting the value of the antiderivative at the limits. And so you substitute y1 plus a2, a over 2, and then minus the function where y1 minus a over 2. And you do the same thing over here, right? The same thing over here. The only difference is that 2, which I've highlighted in green. So all that green color is now sort of embedded in that 2. And then what I did is, in order to make it a little easier to write, wherever you see a dot, you should think I p y over h bar. In other words, I worked with the sign, but I turned this into this little red dot everywhere, so I didn't have to write it so much. It's a little notational convention. And when I did that, I'm basically breaking all 4 of these guys up into products, right? And then when I do that, I notice, I've got these guys, this e to the minus y1 dot and e to the minus y1 dot. Those are constant terms that I can pull out. And what's left behind is a minus a over 2 dot and a plus a over 2 dot, which can be arranged as a sign as long as we multiply by 2i. And we still have to flip them. We have to flip them to get the definition of sign right. So that's where the negative sign comes from. And that's true on both sides. So we end up with that negative 2i there. and then we have sine of a red dot over 2 on both sides. But it's the same function on both sides, meaning both slits created the same function, and both slits have the same width, right? So it's no surprise. If one of the slit was a different width, this A would not be A, it would be B, and in which case we wouldn't be able to just pull it out like this. So we're going to distribute the sine A over 2 out, but we can only do that because they're both the same width. Otherwise, it'd be a lot harder. So we pull out the sine, and I replace the red dot with py over h bar. And you lose the I when you do that. When you obviously we lose the I. Where do we lose the I? So we lost the I in order to create the sine, we had to take the I out of the red dot, right? Basically. So this red dot actually shouldn't even be here because it's not really the red dot. It's the red dot times what? Minus I? I don't know. It's the red dot without the I. So let's call that the green dot, right? The green dot. Regardless, you end up here. And then what's left over here is this y1 and y2, which is I now replace fully the red dot, including the I, the imaginary I, and we end up with this expression. And this total thing is the amplitude, right? This is the amplitude py on gamma, right? And now the total the contribution of each of the slits is right here, right? And notice you're adding them together. You're adding these two contributions. This is where the interference happens now, right? Because this will be a constant, right? This will be a constant. And, well, let's see. Actually not, right? Because this is where, we're going to replace P. So the interference is now kind of blended in here, I guess. But you're really still seeing it. Anything that's being summed, well, okay, the interference is definitely with this sum, but you've got to distribute in the sine as well, right? You've got to distribute this into the two, just like this. This is where the interference happens. That's what I'm trying to say. Okay, so now that we know where the interference is, or now that we know what the amplitude is, calculating the amplitude, that's where the interference comes in. And now what's next is, here's the amplitude. I've written the amplitude again here. No, I don't think there's any changes. And now we're going to calculate the probability density, right? So everything gets squared, then the complex numbers get modulus squared. So this guy squared, h bar, py, a pi h bar, right? That's good. Then this is a complex number, so we have to take its modulus squared. So I'm going to note that and then move on. And then this guy here, oops, I'm missing the squared, right? That guy gets squared because that's a real number. So how do we do this modulus squared? Well, it's just like any complex number. We're looking for z conjugate z, right? Where z is a complex number. In this case, this is z, right? So z times z conjugate. And if you blow that up, you get this times its own conjugate, which is 1. And then you get this times this conjugate, which is this expression here, right? The minus y1 and the conjugate y2 is positive. And then you get this times this conjugate, which gives you the exact same thing, but y1 and y2 are reversed, right? Reversed. And then you get this times its self-conjugate, which is another 1. And then if you look at it carefully, you will realize that the two 1s add together to give you a 2, obviously. And then if you flip this to be y2 minus y1, right, what do you end up? You end up with a minus sign, y2 minus y1, and then you have the structure of exponential I to something plus exponential minus I to something, which is the structure of a cosine, but you're off by a factor of 2. So you take the 2 that was 1 plus 1, you've got the 2 here, and then you've got this combining with this to give you 2 times the cosine. So that will be 2 times the cosine of something. So you pull out these 2's, and that's what this 2 is. And you're left behind with 1 plus the cosine of py over h bar. And this is what we're calling the distance d, right? And that's what d is. And then nothing changes here with this sign. So you're in a pretty good position now. We've got the modulus. Now we've got the probability density function, right? The probability density function. I could write this as, I suppose, probability density of py, right? It's defined as that. Okay, let me clean this up. Okay, and you can make a few notations right away, right? You can see that the distance between the slits is going to matter and the size of the slits is going to matter, right? They're both going to matter a lot. So, and there's going to be attenuation. The higher momentums are going to have less contribution to the density, and the larger the slits are, the less this density contribution is going to affect us. Okay, so what have we got now? Let's look over here. And now what we're doing is we are simplifying a few things. Let me see. Let's see, the first thing I did was I did cancel. There was an h bar squared in the previous screen and an h bar below, so I canceled that and cleaned that up. And then I said, all right, so now we're going to think about plotting this thing. So we call all of this alpha, right? And then this is 1 over alpha squared, and then this is a constant that you would use to multiply by 1 over alpha squared to make sure your coefficient was correct. So you end up with, then, because you do that, you end up with a over 2 pi h bar, which is that, times the sinc function of alpha, right? So this, and remember the sinc function of alpha is just sine squared alpha over, oops, not squared. The sinc is sine alpha over alpha. And sinc squared is going to be the sine squared over alpha squared. And this is alpha squared, and this is a constant to keep us good, so we got this sinc function in there. So that's just a tidy way of writing the function in a nice form. So we got the sinc function now, and then we have the 1 plus cosine, and now I've substituted for py, right? The sort of established idea that py equals the momentum of that incoming wave times the sine of the scattering angle, right? So now so I guess what I should say is it would be a mistake to think that that was some kind of differential, right? dp, right? That's not what it is. It is the distance between the slits, right? That's what d is. And p sine theta, that's py. So that's this substitution, just a simple substitution for that. And then I'm going to make a few other substitutions. The first thing I'm going to do is I'm going to take note of this trigonometric identity. 1 plus the cosine of some angle is equal to 2 times the cosine squared of that angle split in half. So I'm going to now define phi over 2 to be everything in here over 2. And if I look at this guy, I have momentum h bar. So I turn h bar into h over 2 pi, and then I have momentum over h, which is the de Broglie, 1 over the de Broglie wavelength. So now I end up with d divided by the de Broglie wavelength, which is this, and then I have this 2 pi in the denominator of the denominator, so those 2's cancel and pi comes up, and I end up with phi over 2 is d over lambda pi sine theta. Phew. Then I kind of do the same thing for alpha. I know I've already substituted into alpha, but now I'm going to unpack alpha again and perform the same process, right? A is the width of the slit, p sine theta is what py is, and then I'm very interested in the de Broglie wavelength because that's the characteristic wavelength of the physics, right? And so p over lambda becomes 1 over the de Broglie wavelength. I have a over the de Broglie wavelength. And then the 2 pi that defines h bar cancels with this 2, and you end up with pi. So you have a over h bar pi sine theta. So it's kind of neat, right? The two trigonometric functions are dependent on the distance between the slits measured in units of the de Broglie wavelength and the width of the slit measured in units of the de Broglie wavelength times pi sine theta, right? So that's really elegant. So if we now just define, A prime is A in units of the de Broglie wavelength and D prime is D in units of the de Broglie wavelength, this ends up being our final result for the probability density in terms of the scattering angle theta. And take note, this constant here is a little different from his, and I'm not sure if I added a square root of 2 or if he forgot a square root of 2. I'm not going to assert the definitive results on that point. Okay, so let's plot this and see what it looks like. And so here's the plot using Mathematica. This is the function. Now what we've done is this part here is gone. So this is just normalized to 1, as you can see right there. And quite a beautiful thing. Should be the same conditions as Mr. Masella used in his paper, right? So we've chosen A prime, meaning the slits are exactly the same width as the de Broglie wavelength of the electron. And D prime is 4 times the de Broglie wavelength of the electron. And the curve seems to match. In his paper, he doesn't have a normalized axis. That's always sort of a problem with these things. And there you have it, right? You have this beautiful interference fringes, and the extent of these fringes is totally due to the double slit, right? We saw the Fraunhofer diffraction didn't demonstrate nearly as much fringing, and certainly not as aggressive fringing, right? So this is very significantly different. And then I think I did it one more time. Yeah, so this one I kept the scales. Sometimes what you'll see is a plot where they sort of cut it off here, and that the intent of that is to blow these guys up so you can see this a little bit more. But in this case, the slits are, if you look, the A prime, A prime equals 4.5 lambda, and D prime equals still 4. So we've just made the slits a lot wider. And what's interesting is when you make the slits wider, you still have this intense narrow spike, but a lot less intensity gets modulated in the interference. And you also notice, if you look carefully, you'll see that even in between the interference patterns, you get this sort of little rise and drop. Not that it's that interesting, but the point is this is the double slit. Now I guess I could experiment with things like I could make D a lot smaller or a lot bigger and play around with a lot of the variables. I mean, once you've got this function in Mathematica, you can kind of do anything you want with it. But what we would learn is that the closer to that the double slit looks to a single slit, the more similar you're going to get everything should continuously deform into everything else. Okay, so there you have it. That's the double slit done with the full mathematics. Let's review. We started with the overall experimental setup. In the beginning I said there's a fundamental length, and I implied that that fundamental length was D, but that's not. I forgot to mention the fundamental length is the de Broglie wavelength of the electron. The fundamental length of the problem is established by the momentum of this electron, right, which is wrapped up in its mass and its velocity, right? So that is an important point to note, is that the scale of everything really depends on lambda. So, but D is sort of this geometric issue, right? Making sure that we have this one theta. So we set up the problem, but we noticed we're going to have a wave function that was uniform over two slits. So we split the big wave function into two little wave functions, but each of these is a wave function for the slit, but the total wave function is the superposition of these two. But notice, these are not basis states. Just because you decomposed gamma into two wave functions, you didn't decompose it into two basis states, right? These guys do not span the entire possible state of physical states you could create for this electron. So they don't count as basis states, right? But we can decompose the two slit wave functions psi and omega into the basis of position basis on the y-axis. From that, we derive the probability amplitude for measuring a momentum y, and that's where the interference happens. I keep pointing out that this is the amplitude, right? Where what we're not doing is this, right? We're not doing that. We are adding and then taking the amplitude, right? And then what happens next? What happens next is then we find, we went through all the math, blah, 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 went through all the math, and ultimately we landed on this expression here for the probability density. We check our units, it's 1 over momentum, so we now know that we can use our interpretation that the probability of finding Py between the values, say, P1 and P0, that probability is going to be the integral from P0 to P1 of Py omega squared dp, right? Or dpy, I guess. And therefore, this guy has to have units of 1 over momentum. And that all worked, and then we looked at some pretty graphs of the result. Okay, so that finally cleans up the double slit using the Dirac Formalism, which I think is fair. I think we kind of pushed the Dirac Formalism all the way through this problem, so that's good. And now we will move on to some different topic. I'm not sure which one, but I have some ideas. And so I'll see you in the next series of prerequisite topics.